Children, today we are going to discuss properties of SO2 and SO3. Continue our previous video class. Now your SO2 reacts with NaOH to form sodium sulfite, which is further reacts with excess of SO2 to give finally sodium bisulfite or sodium hydrogen sulfate. So that is why SO2 reacts with NaOH. First your formation of sodium sulfite, further reacts with excess of SO2 to give finally sodium sulfite. Next, it reacts with chlorine in the presence of charcoal. It acts as a catalyst to give SO2Cl, that is called sulfuryl chloride. So then the reaction is SO2 plus Cl2 gives rise to SO2Cl. This is called sulfuryl chloride. It also acts as a reducing agent. That's why it undergoes oxidation. That's why it oxidizes to sulfur dioxide. SO2 here undergoes oxidizes in the presence of vanadium pentoxide. It acts as a catalyst to form sulfur dioxide. So that is called SO3 formation. Next, so the structure of SO2 molecule, it exists as the resonance structures or canonical forms. These two are canonical forms of SO2 molecule. Now children observe here, in SO2 molecule, here 2 sigma bonds and 1 pi bond. Here total number of lone pair of electrons are here 3, here 2, 5 plus 1, 6 total lone pair of electrons in SO2 molecule. And finally, in SO2 molecule shape is angular structure or angular shape. Your bond angle is less than 120 degrees. That is called 119.5 degrees only. But it undergoes hybridization is sp2 hybridization. Shape is angular shape. Bond angle is 119.5 degrees. But bond length in between your S double bond O is 1.43 angstroms, children. These are the properties of sulfur dioxide. Next, what are the uses of sulfur dioxide? The main use of here refining of petroleum as well as sugar using for the SO2, and also it is used as a bleaching agent for silk and wool purpose. It is also used as a anti-chlor, means removal of excess of chlorine present in the fabrics. That's why especially it is used in textile industries. Here excess of chlorine is present in the cloth or fabric removed by using SO2. Because of it acts as a anti-chlor agent as well as disinfectant also and preservative. Next, liquid SO2. Actually SO2 is a gas. In liquefied form of SO2 is used as a solvent for organic as well as inorganic matters. So these are the uses of sulfur dioxide. Next, one more important compound here, trioxides, SO3, that is called sulfur trioxide. It can be prepared by sulfur dioxide is what happened? Oxidized in the presence of vanadium pentoxide to form the SO3. Here the formation of SO3 is a exothermic process. Exothermic process. And also it is a reversible reaction. That's why you are using Lee-Chatelier principle also, children. You are based on your Lee-Chatelier principle, your low temperature and high pressure is required. Why? Because your number of moles are 3 moles, but number of moles are here 2 moles. As per Lee-Chatelier principle, your low temperature, high pressure, the reaction should be processed in the forward direction to give good yield of sulfur dioxide. In this process, using either catalyst V2O5 or nitric oxide or platinized asbestos, anyone is choose the catalyst for children. That is the preparation of SO3. So at room temperature, here all trioxides are solid only. Like that, here SO3 is also one of the solid, but it exists as the 3 distinct forms, 3 different forms. These 3 different forms are named as alpha form, beta form and gamma form. But alpha and beta forms are linear structures. But gamma form is a cyclic form structure. In this cyclic form, SO3 molecule exists as the trimer state children. Trimer in gamma form. But there are the alpha, beta and gamma form. Which is the most stable? Alpha form is the most stable. Here alpha form is especially exists as a crossed linked structure. Crossed linked structure. And also here the sulfur dioxide is an anhydride of sulfuric acid children. Suppose here remove a water molecule from H2SO4, then what happens? Here the formation of here sulfur dioxide. Otherwise sulfur dioxide dissolved in the water, again it gives rise to that H2SO4. So SO3 is dissolved in the water, gives rise to sulfuric acid. But industrially, it is very difficult because of a large amount of heat is liberated. It sometimes explosion also takes place. That's it. Very carefully doing, but industrially, it is not possible. Only in the laboratory, here sulfur dioxide is dissolved in the water, gives rise to sulfuric acid. But industry here, how we are prepared? Sulfur dioxide is dissolved in first H2SO4 to gives rise to oleum. Oleum is further dissolved in the water, gives rise to sulfuric acid. That's why here the sulfuric acid is prepared by indirectly from sulfur dioxide, but not from directly. Because of the process is here, exothermic process, a large amount of heat is liberated. So industrially, it is not possible. Okay, children. So then here is the monomer state of sulfur dioxide. It exists as a structure is trigonal planar structure. It consisting of 3 sigma bonds. Here 3 pi bonds are formed. Out of 3 pi bonds, here 2 pi bonds are formed by p pi d pi bonds. Children, very important. In SO3 molecule, which type of pi bonds are present? 2 are p pi d pi bonds and 1 is a p pi p pi bond. Children, 3 are sigma bonds. Here the shape is triangular planar shape. It undergoes sp2 orbitration. Bond angle exactly 120 degrees. In previous also discussed, SO2 molecule also sp2 orbitation. But shape is angular shape. But here the shape is triangular planar shape. Bond angle here less than 120 degrees. Your bond angle is 120 degrees. Why? Because here there is no lone pair of electrons. That's why there is no distorts the shape. But here one lone pair is present. Due to lone pair bond pair repulsion, the shape changes from triangular planar to here angular shape, and bond angle also reduces from 120 degrees to 119.5 children. So, to remember your structure of SO2 molecule and SO3 molecule, your SO2 molecule exhibits only here which type of bonds? There 2 pi bonds are there. There 2 pi bonds also. Here one is a p pi bond. 2 pi bonds, and one more is here p pi and d pi bonds in SO2 molecule. But this is SO3 molecule, 2 are p pi d pi bonds, one is p pi bonds. Very important. Which type of bonds formed in SO2 molecule and SO3 molecule, children? So that is the structure of SO3 as well as SO2 properties. Children, now we are studying about action with halogens. Here, the 16th group reacts with the halogens to form various types of oxides like M2H2, MX2, MX4, MX6 as well as other halides also. Your M2H2 is called monohalides but exists as the dimer. That's the representation is of M2H2. Monomer state is MX only. Monohalides. Here dihalides MX2. MX4 is tetrahalides. MX6 is hexahalides and here other halides. So here given each element examples. Oxygen forms only monohalides and dihalides. Does not exist tetrahalides and hexahalides. Why? Because absence of d orbitals. But sulfur, selenium and tellurium, it forms mono, di, tetra, hexa as well as some other halides. Here gives the list of various types of halides. So for example, sulfur, formation of sulfur monochloride, sulfur monochloride, sulfur dichloride, sulfur dichloride, sulfur tetrachloride, sulfur tetrachloride, sulfur hexachloride, and others also. So like that, tellurium, selenium also forms, including polonium, also forms the various types of halides. Now, a study of each one. First one can take here monohalides, that is in the dimer formula M2X2. Here examples are oxygen, monochloride, sulfur monochloride, here sulfur monochloride, but exist as dimers. Now, can take example here, oxygen O2F is the dimer of OF, monochloride formula OF. It is a reddish brown gas. It is acts as a oxidant as well as fluorinating agent. Fluorinating means you have more affinity of fluorines. That is called fluorinating agents. So the O2F2 molecule structure is similar to H2O2 molecule. You are studying first year. What is the structure of H2O2? It is a non-planar, non-linear, open book structure. So that is the similar to here. This is a open book structure. This is in book or open. Is the oxygens are occupying the spine of the page. Here fluorines are occupying the cover pages. Fluorines. Here the oxygen atoms is linkage is OO linkage. Like H2O2 also OO linkage, and here hydrogens and hydrogens. Now that's why the structure is similar to H2O2. Here the oxygen atoms are undergoes what is the hybridization, children? sp3 hybridization. Next, how to preparation of your oxygen monochloride? It is prepared by pure fluorine and oxygen gases in dry form, passed into the silent electric discharge tube at low pressure to form the oxygen monochloride. That is the preparation of oxygen monochloride. Like sulfur monochloride is prepared by excess of sulfur reacts with the dry chlorine gas to form sulfur monochloride. Again, this sulfur monochloride is dissolved in the water or reacts with the water. What happened? Here liberation of sulfur dioxide gas also. Like that, here selenium monochloride. Selenium monochloride is unstable. Here dissociate into formation of stable selenium tetrachloride and also a formation of selenium. It is one of the example of disproportionation reaction, children. So that is why selenium monochloride involved in the disproportionation reaction. One component is selenium tetrachloride, one more component is here selenium. Here selenium tetrachloride oxidation state is +4, here selenium oxidation state is 0, here selenium oxidation state is how much? +1. But what happens? Here +1 to +4 oxidation, +1 to 0 reduction. So only one reactant element of selenium undergoes both oxidation and reduction takes place simultaneously. That is why it is called a disproportionation reaction. Now children, we are discussing about the dihalides. Dihalides examples: oxygen dichloride, sulfur dichloride. Now your first point, we are discussing about the OF2, oxygen dichloride. It is a pale yellow poisonous gas. It dissolves in water and as well as a large amount of evolution of oxygen gas also. So here fluorine reacts with sodium hydroxide, nothing but caustic soda, as a dilute or concentrate. If reacts with the dilute NaOH, one of the product is oxygen dichloride along with the sodium chloride and H2O. In case of concentrated NaOH, the product is again here O2F2, oxygen monochloride along with the sodium chloride and H2O. Now you observe children, action with NaOH, dilute solution, OF2 is formed. Action with the constant NaOH, O2F2 is formed. The main products. Byproducts are sodium chloride and H2O. Here, OF2 molecule is similar to H2O molecule. That is angular structure. It undergoes hybridization sp3. Like SCl2, sulfur dichloride, it can be prepared by sulfur monochloride reacts with trichlorine at room temperature to form sulfur dichloride. It is a dark red liquid and foul smell also. It is also a hybridization is here sp3 hybridization. Shape is angular shape. It is also similar to H2O molecule. Next, MX4 tetrahalides. The best examples are here sulfur tetrachloride, sulfur tetrachloride. But the preparation of sulfur tetrachloride is very difficult because of it is also a fluorinating agent as well as oxidant. So here form the stable SF6 molecule hexafluoride. But sulfur tetrachloride can be easily prepared. It is prepared by sulfur reacts with dichlorine, sulfur tetrachloride is formed. So either sulfur tetrachloride, both are distorted tetrahedral shape. Both are undergo cyclic atoms sp3d hybridization. Here one is a lone pair of electrons, 4 are bond pair of electrons. Total 5 electron pairs. That is why here hybridization is sp3d. So sp3 hybridization means we expected as trigonal bipyramidal. Due to lower pair of electron, the shape is distorted. That is called distorted tetrahedral. The lower pair of electrons occupies any one of the equatorial position, children. This is the equatorial position, or this is the equatorial position. This is the equatorial position. But these two are axial positions. Here lower pair is occupying always here equatorial position. Equatorial positions are always nearer to the central atom. Axial positions are always far away from the central atom. So either sulfur tetrachloride or sulfur tetrafluorides, both are distorted tetrahedral. It undergoes sp3d hybridization. Like that, here SF4 is a gas, but whereas SeF4, selenium tetrafluoride is liquid, tellurium tetrafluoride is a solid. Here, what I mean, change the central atoms, increasing the size. Here, the physical state also changes from gas to liquid, liquid to solid. Next, hexahalides, MX6. The best example is of SF6. It is the most stable form of sulfur fluorides. It is a colorless gas. It does not undergo hydrolysis. Why? Because SF6 is the stable form. There is no further undergoes hydrolysis. Especially this gas is used in high voltage gadgets. Next, this SF6 molecule is a octahedral geometry. It undergoes sp3d2 hybridization. The bond angle is how much? 90 degrees, children. So in finally, always MX6 are octahedral, MX4 are distorted tetrahedral, MX2 are angular shape, but M2X2 are open book structures. This is important for children. Shape of the molecules. Now let us go to study of oxygen. Now you study of preparation, properties and uses of oxygen, children. How to preparation of oxygen? Here 4 methods are there. Then the first method, in the laboratory method, it is prepared by heating of oxygen salts like chlorates, nitrates and permanganate salts are heating to form the oxygen gas. Second example can take chlorates. That is the potassium chloride. On heating, decomposes to potassium chloride and oxygen gas is liberated. Like one more method, thermal decomposition of metal oxides. Especially they are using low metal oxides or some high metal oxides in the electrochemical series. So example, we are using silver oxide, mercury oxide, lead oxides are using to liberation of oxygen gas. Next, one more method, decomposition of H2O2 also gives rise to oxygen gas. But whereas in large scale preparation of oxygen gas by using electrolysis method only, electrolysis of water. Here also pure water is a poor conductor. That is why we are using acidified water or alkaline water. Now in electrolysis, here the hydrogen gas is liberated at cathode, oxygen gas is liberated at anode. So the large scale preparation of oxygen gas by using electrolysis of water. That is the preparation method, children. Next properties. You know, oxygen gas is a colorless, odorless gas. It is a highly soluble in water. That only due to dissolving of oxygen gas in water, you are living off aquatic animals like fishes, ponds, like that. And also, you know, according to MO2 theory, your oxygen molecule is a paramagnetic nature, but normally it is a diamagnetic nature as based on electrons. Your O2, total number of electrons, 8 plus 8, 16. That is even number. It expected as diamagnetic, but according to MO3, it is a paramagnetic nature, children. Next, it reacts with most of the metals and as well as non-metals, but exception of your noble metals like platinum, iron, even noble gases. There is no reaction with the oxygen gas. But here, oxygen is the due to high electronegativity, that only here reacts with the most of the metals as well as non-metals. Exception for noble metals like platinum, iron, or even noble gases. So examples are given some metals, calcium, aluminum. What happened to form the corresponding oxides? Calcium reacts with oxygen, calcium oxide. Aluminum reacts with oxygen, aluminum oxide. Like zinc sulfur reacts with oxygen, zinc oxide. Hydrochloric acid reacts with oxygen, chloric gas liberator. Methane reacts with oxygen, carbon dioxide and H2O. So these are examples of your properties of action with metals and non-metals. You know what are the importance of oxygen gas? That is useful for respiration system as well as it is useful for combustion of organic substances. Next, it is also one of the use for using oxyacetylene gas cylinders for welding purpose in steel industries, and also oxygen cylinders are used in hospitals. That is also one of the use for here. So these are the preparation, uses and properties of oxygen, children. Now children, the study of ozone molecule. It is one of the allotrope of oxygen. So it is prepared by pure and dry oxygen gas is passed into the silent electric discharge tube to form the 10% of ozone only. The left out the 90% of oxygen. That's why here the formation of the product is O2 plus O3, 10%. Ozone, 90% oxygen. This mixture is called ozonized oxygen. Here the formation of ozone into the mid process as well as reversible method. So as per Decomposition principle, due to endothermic reaction required for high temperature, as per number of moles, your product cells are less number of moles than reactants are required for high pressure also. That is why as per Decomposition principle, which are favorable conditions? High temperature as well as high pressure. But in this process, here the formation of ozone is 10% only, remaining 90% oxygen. But how to get separated ozone gas from oxygen? That's why the mixture of ozone and oxygen is further passed through silica gel substance. In this process, ozone is absorbed by silica gel, but oxygen gas is leaving out. Then further, here passed into the nitrogen column. What happens? Here oxygen gas, ozone gas is separate out from nitrogen column. Therefore, to obtain the pure form of ozone gas, children. Next, here ozone pure form is a pale blue color, pure form of ozone, and also it is a pungent odor as well as poisonous gas. Whenever inhaling, it becomes the effect of respiratory system also, children. That's why it is a poisonous gas. It is mostly dissolved in organic solvents like carbon tetrachloride, turpentine and acetic acid. But here very slightly dissolved in water also. So it is here the ozone formation is unstable. That is why here ozone molecule is spontaneously dissociated into stable form of O2 molecule. That's the conversion of ozone to O2 is here exothermic process, children. So that's why here as for thermodynamic data, conversion of O3 to O2. Here exothermic process, that's why delta H is negative, and also it is a what happened, disorganization what happened, increases. Both are gases absorbed here. Ozone is 2 moles of gas, oxygen is 3 moles of gas. Number of moles what happened, increases. That's the randomness also what happened, increases. That's why delta S becomes positive. But this process is spontaneous. Therefore delta G becomes what happened, negative. It is very important, children. The decomposition of ozone is a delta G, delta H and delta S. What are these symbols here? Delta H is negative, delta G also negative, but delta S is positive, children. Next, here the decomposition of ozone is very easily, whereas decomposition of ozone what happened? To releasing of nascent oxygen. So you know, nascent oxygen means just readily releasing of oxygen. That's why this nascent oxygen is very highly reactive, unstable. This due to cause of liberation of nascent oxygen, it acts as a oxidizing agent as well as bleaching agent also, children. So that's why here ozone is one of the powerful oxidizing agents. So due to oxidizing property, what happened? Here lead sulfide is a black color. Black lead sulfide here undergoes oxidation converted to white lead sulfate, children. As well as here potassium iodide moisture means potassium iodide solution reacts with the ozone gas, liberation of iodine. This liberation of iodine is further titrated with the standard solution of hypo. Is one of the estimation method for the quantity of ozone. What is the method? Estimation of ozone. How to estimation of ozone? How much quantity of ozone is required for the oxidation of potassium iodide? Using the method here, the liberation of iodine gas is further titrated with the standard solution of hypo. On the basis here to estimate the ozone gas. This is also one of the oxidizing property. Next here, nitric oxide reacts with ozone. What happened here? Converted to nitrogen dioxide. And especially in the stratosphere, supersonic jet planes are here releasing of the gas consisting of nitric oxide. So you know, here stratosphere only ozone gas is present, ozone layer. Due to releasing of nitric oxide from supersonic jet planes, the ozone gas reacts with nitric oxide, immediately converted what happened? Nitrogen dioxide. Therefore what happened? Here ozone is converted to oxygen. Therefore here the ozone layer becomes depletion takes place. That is why in nowadays the supersonic jet planes are banned in stratosphere. Why? Because the releasing of the gas reacts with the ozone converted to nitrogen dioxide, ozone converted to O2. Therefore depletion of the ozone layer takes place. That's why banned the supersonic jet planes in stratosphere, children. Next here, what about structure of ozone molecule? Here, ozone molecule is an angular shape. It is also exhibits the canonical structures. It consisting of here 2 sigma bonds, 1 pi bond. The total number of here lone pairs are here 2, here 1, 3, here 3. Total 6 lone pair of electrons in ozone molecule, children. Here the bond angle is nearly 117 degrees. And bond order becomes here how much? 1.5 bond order for ozone molecule. Next one. But what about the uses of ozone? You know, here ozone is one of the powerful oxidizing agents as well as bleaching agent, and also it is disinfectant and kills the bacteria. That's why here the purification of water or sterilizing of water, here ozone gas is used. Just children, you observe in water bottles in market, here using of water bottles are using as ozonized water. Nothing but here sterilizing of water is using ozone gas. That is called ozonized water. And also it is acts as oxidizing agents as well as reducing agent also, children. Especially the ozone gas is used for the manufacture of potassium permanganate and artificial silk also. So these are the uses of ozone gas, children. So here the most important oxygen allotropes are O2 and O3 are studying here, children. Okay.